Welcome to day 2 of Connected Health 2015. I don't know about you, but I had a great day 1. And it's stimulating in so many ways, and I know I met a lot of new people. I hope you did too. Today is going to be every bit as good as yesterday. And the first 2 speakers are from the MIT Media Lab, and they're kind enough to join us despite the fact that this is the 30th anniversary of the lab, and they have a lot of obligations back just over the bridge in Cambridge. So I'm going to be brief in my opening remarks so that we can get going and have their wisdom and then release them back to their own celebration. But I urge you today to check out the poster session. There's going to be a lot of really interesting content this afternoon. We have 2 speakers from Partners. My boss, Greg Myers, closing out. Right before him, O'Neill Britton, who oversees all of our e-care implementation. You sure want to stay around to hear both of them. And there will be book signings. I'm signing books at noon. So lots and lots of good content today, and we really had a good day yesterday. I hope you had fun last night. Now, without further ado, the first speaker is Joi Ito, who's the head of the MIT Media Lab, and he's going to be interviewed by R.D. Sahl. So I'm going to now turn the podium over to R.D. Good morning. Thank you.
Thank you, Joe. Joy. Good morning, everybody. I hope you're caffeinated and connected for day 2 as we continue our series of keynote conversations. As Joe said, our first guest this morning is Joi Ito, director of the MIT Media Lab. But he's so much more than that. He's an activist, an entrepreneur, a venture capitalist, a champion of emergent democracy, sits on the boards of Sony, the Knight Foundation, the New York Times, and is chairman of a very interesting enterprise called Puuretech, and it's one of the things we'll be talking about this morning. Ladies and gentlemen, Joi Ito. Joi, good to have you here. Early start, and actually a very, very important day, the 30th anniversary of the MIT Media Lab.
Yes, I've been there for 5 years, and originally it was supposed to be on a different day, but Nicholas Negroponte, the founder, insisted that we had to have the 30th on the 30th. So.
All right, well, we promised to get you out on time because I know you have a busy day ahead of you. You've said that the key to innovation is being what you call a nowist. What do you mean, and how does that apply to what we're talking about here?
So it's partially a pun. I work with a lot of people who call themselves futurists. And I think that predicting the future is becoming more and more of a futile attempt. I mean, I think you can see trends, but I think what's more important than anything is being perceptive of what's going on now and being able to respond to and integrate with what reality is at the moment. And it also ties into this notion of presence in the mindfulness perspective. But I think what's essential really is to, whether you're talking about designing an intervention or whether you're talking about trying to understand, come up with a strategy, I think instrumenting the world, instrumenting our bodies, instrumenting everything to have maximum awareness of your current situation is probably much more important than coming up with a 20-year roadmap, I think.
The zen of living in the technological moment, I guess.
That's it.
From all of the sessions over the last day or 2 here at the Symposium, it's clear that medicine and technology are coming together. I guess the question I have is, are they colliding or converging?
That's a good question. I mean, I think there is a collision. I think that when you look at the number of disciplines that are now involved in or useful for thinking about, whether you're talking about research, therapeutics, or diagnostics, the number of disciplines involved is increasing substantially. More broadly in life sciences and bio, and more specifically in medical. And I think that the traditional sort of peer-reviewed, disciplinary, federal-funded research model is too narrow, considering the things that we need to bring to bear. And I think that whether you're talking about research universities or federal funding or even some of the large companies that traditionally were in this space, they're ill-equipped to bring in the kind of talent or thinking that we need in order to bring these things together. So the collision would be that we're not, I don't think we're structurally well designed right now to take advantage of all the technology.
Let me come back to that peer-reviewed research model, the research university model. That model exists for a reason, to assure that there's good science, that there are replicable results. That seems to be, according to what you're saying, there's some push and pull, some tension between that model and the innovative model represented by many of the people here.
Yeah, I think so. You know, if you look historically, disciplines have evolved, have merged, have sort of created, but the speed at which a discipline can evolve is quite slow because it requires a sort of a natural sort of genetic shift. But right now, when you look at, say, take synthetic biology and you look at MIT, most of the heads of the labs are computer science people. And that synthetic biology is becoming sort of an engineering computer science discipline. And what's hard is, or you look at our lab, Ed Boyden's lab that's working on the brain, you have people working on nanorobots and computational optics and synthetic materials and chemistry, and they're all in this lab working on tools on how to interrogate the molecular level imaging of the brain, for instance. And those sorts of tools, if you're in a traditional academic discipline, it's very difficult to get, one, funded, and two, issue PhDs to people who are sort of in between these disciplines. And what's fascinating is, you see, for instance, like one of our kids is working on a device that uses a synthetic, it's a bacteria with a synthetic plasmid to do sensing, and then he uses a electrical circuit to sense the voltage change to then send a signal to the computer. And he said, well, I could have made the sensor in solid state, but I realized it'd be more efficient to use a biological device. But for the wireless network part, it's obviously going to be a circuit, and over here we're going to do this. And to him, the biology and the circuits are completely fungible. They could use either one. And it's not easy inside of a university to take a kid like that and say, well, you're sort of half an electrical engineer, you're half a synthetic biologist, and you're going to get a PhD in what? And it's the same with the funding. I think with the federal funding, it's sort of an extension of the peer review system. So there's that. There's just the failure to cover the spaces between the disciplines, which is really rich with potential. And then also just fundamentally, I think that the way that even the peer-reviewed system, I think Daniel Kahneman wrote an article in The Economist about this, but then that kind of kicked off a whole public debate about, whether our science is, some of the seminal papers haven't been reproducible. The data isn't being shared, and so there's another layer, which is now that we have all of these networks and this cloud and the fact that doing these little pipetting by hand, I mean, is that the right way for us to be creating a corpus of knowledge that we can share? So I think there's also a question fundamentally about how we do science.
Let me stick with science. We're pretty good now at gathering data.
Yeah.
The step where we probably need advancement and some work here is on interpreting data and using data, which brings in this concept of artificial intelligence. And I know you're thinking about this.
Yep. Yeah, absolutely. And I think, so there's multiple layers. There's the data, the patient data, and using machine learning to help make the system more efficient, more effective. There's again, research, therapeutics, and diagnostics all can use artificial intelligence. But I think, so two things. One, for most of you probably know what machine learning is, but just to be very clear, machine learning is very different from algorithms in that algorithms, you sit and you write the rules, and the computer follows those rules. Machine learning, you set up a system, and it's usually a computer science person, and then it ingests data, and then it takes the data and starts to look for correlations, not causalities, but correlations, to try to be able to predict what the right answer to a particular question might be. But you can't go in and read the code of an AI. There's no algorithm to read it. So you interrogate an AI very much like you would interrogate a human being. And and I only raise that because there are some really interesting ethical questions about what data you use to train the AI, and how you interrogate and manage the AI. And this is sort of a slightly separate topic, but I wanted to just raise that because I think it's important. But I think there was an announcement recently that Watson is sort of almost finished with med school, right? And just and I think it's sort of a joke, but sort of true that I could imagine Watson being able to ingest all of the data that would traditionally be given to a student in med school. Now imagine if you had a computer that had all of the knowledge that you needed from med school, and if it were available all of the time. Maybe there's an argument to be made that you don't have to memorize it if it's available all the time. I remember when I was in 5th grade, I had to argue with my father about getting a calculator. I'm turning 50 next year, so this is the first calculator that was on the market. And he wouldn't buy it. He says, you're not gonna know how to do long form division. And I said, Dad, I want to compute astrophysical formulae like orbits. Did you do that in 5th grade? And he said, no. And I said, because you didn't have a calculator. And he finally let me buy this calculator. And I think it's kind of similar. I think that the fact that we spend so many years of MD's life sitting around trying to memorize things that a computer might be better suited to memorize, maybe you can spend those years teaching them how to make a patient feel more comfortable, read signs and symptoms, or maybe increase the number of people who are allowed to interface between the medical system and the human being. And I think, to me, there's a whole argument about computers taking our jobs, but I think it's sort of the opposite. I think that the computer-human combination will be a winning team, and that medicine is going to be one of the primary places to benefit.
This dovetails very nicely with what Vinod Khosla was saying yesterday about machines, tech taking over 80% of what a doctor does, making the 20% more useful. In the model you're talking about, that human component becomes even more valuable.
And I think one of my favorite stories it's an old book, but Herb Benson's book, Relaxation Response. And I might get this quote not exactly right, but he's about to go to Tibet to study Tibetan medicine and explains the methodology to the Dalai Lama. And the Dalai Lama says, you're not going to get any results because 80% of Tibetan medicine is a relationship between the doctor and the patient, and you call this the placebo effect, and you're going to control it out. But that is Tibetan medicine. And I think what's interesting is we're looking always in traditional medicine for that like one molecule that does this magic thing, forgetting that 80% or something like that is all about how you feel. And so if we could shift the work that we're doing into that space, which where humans are sort of instinctively good at, but I think, and now I don't want, this gets into slightly politically incorrect territory, but like if imagine going through the whole medical system and getting that certification to be a doctor, you don't have a lot of energy or time left to, it's also looking at the patient ratios and things like that to provide that 80% bedside manner.
Let me stick with AI for a moment. That's not only about science, but adapting that and using it and believing in it is also a leap of faith at some level, isn't it?
It is. I think that the thing that we have to remember is that artificial intelligence will only be as smart as the data that we provide it. But it can be smarter about more data than we can because it can process a lot. But for instance, this isn't a medical example, but just to take so in the smart cities thing, one of the applications is to try to create models that predict crime. And if you ingest all of the criminal arrest records and things from New York City, well, you're going to get a bias against African Americans because of the stop and frisk rules and the way that the policing works. And so you're just going to reinforce the systemic biases if you just ingest biased data. And there's a funny joke which may or may not be true, which is if you train a car, self-driving car in India, that you probably need several months of cultural training before it should be allowed to ride on the streets in the US. And so I think that what's interesting is AI will also have cultural and ethical biases because just as we day to day are always fighting against conflicting value systems, it's going to happen. So the other conference, I was just on a mailing list with a bunch of our computer scientists, and they were saying that if the Volkswagen car that had that EPA thing had an AI, it probably would have cheated too. It probably would have said, when my wheels are straight and the bonnet's open, here's what I do. But if the person I'm driving is late for an appointment, here's what I do. And that there's no easy way to sort of force an AI to be,
Yeah. I want to turn the corner to what you're doing at Puuretech.
Yep.
A new VC effort in biopharma, but with a new approach to it. Tell us about it. What are you doing? What's different?
So, what's different is it gets back to this this question that I have about the tradition, just doing it inside the traditional disciplines. I think we have a board and a group of scientific advisors and associates who are from all kinds of fields. And we look at the somewhat traditional but important medical problems like mental health or obesity. And then what we do is we try to look for all kinds of research that might have an effect. So, whether it's video games or new polymers or materials, or going back and looking at old drugs and doing unique things to them. And I think the key is that we have people who have permission to think outside of traditional funding models. And this is and unlike VCs, I think we believe that you have to build some of these companies, not all of them, but some of these companies take some real time and real science before
you call them disruptive approaches.
Yeah, I think they're very disruptive. It depends from whose position you're looking at it, whether they're disruptive or not. I personally, because I come from Silicon Valley and I come from the internet startups, to me they look somewhat traditional in that what you're doing is you're looking for that unique space that you can move in very quickly because you have a combination that isn't traditional. So I would say non-traditional. But I think they are disruptive from the perspective of the traditional ways.
So give us for instance, what are you working on?
So for instance, the one that I was involved in very early when I joined the organization was a company called Achille. And it was sort of the first idea was, well, could we use computers or video games to do things to the brain, now that we're starting to understand more about neuroscience, to affect things like ADD or schizophrenia or Alzheimer's. And we met many researchers. This is the great thing about the Puuretech model is we have access to so many wonderful people. And we met Adam Ghazaleh at UCSF, who has been working on the sort of relationship between games and neuroscience. And he had done this thing called NeuroRacer, which showed basically what you're doing is you have to kind of have a motor control of something, and then you have some pattern recognition. And he showed that if you are forced to do this multitasking, it loads a particular part of your brain that deals with things like interference. And by playing the game for a certain amount of time, you can start to increase the ability for people to do multitasking, which affects things like recall and so on.
And that's independent of just getting better at the game.
That's right. And I think that's the key thing, is that a lot of these games, these brain games, are designed by game designers who make things that seem like they'll make you smarter, but they're not based on sort of real neuroscience. And so most of the games that you see just make you better at the game, whereas we have shown a variety of effects that are long-lasting. So some of Adam's original work show persistent effects 6 months later with very slow degradation. And I think the key is that we're doing FDA trials, and we're working with the medical community. And so I think there was recently a paper signed by a number of neuroscientists really bashing this brain game industry for sort of selling snake oil. And I think that again, bringing in real science and real medicine and clinical studies together with this emerging field is really fascinating.
So to come full circle, I'm going to ask the nowist to be a futurist for a moment. What does the world of connected health look like in 10 years, 20 years?
So this is a perfect example of where it's hard to be a futurist, because I feel like the potential of the technology is tremendous, but it won't be deployed unless we somehow fix some of the broken incentive models. And I actually will credit Ronald Reagan for this quote. He has a wonderful story about how rodent exterminators have an incentive to reduce the number of rodents but not eliminate them, because if they eliminated them, they would be out of a job. And I'm worried that a lot of the people who are core to the system of delivering medicine have some sort of incentive of delivering fixes, but not necessarily of eliminating all of the problems. And I think that we bring, and so in that sense, bringing different industries and different players, people like Google, people like other, all types to sort of fiddle with the business model, I think is also important. And that I can't predict when that's going to happen, because that involves a lot of things that don't have anything to do with technology. But I will say on the technology side, we are understanding more and more. And I think that there is more and more adventurous funding going into those spaces that weren't traditionally worked on. And I think that we are understanding the human body in fundamentally new ways. And so especially in the area of predictive medicine, personalized medicine, and fully integrated. So in consumer electronics, we often talk about human-centric design. And yesterday I had a panel with some of my my faculty, and Hugh Hare, who works on bionics, said, well, real human-centric design is when we really understand the human body and we create devices and technologies that are extremely well-tuned, not just to our sort of conscious user interface, but to our whole bodies. And I think that all of technology should be fully integrated with medicine.
And on that here and now note, we will thank Joi Ito for being here today. Congratulations for all the work you do at the MIT Media Lab and for spending some time with us. Joi Ito.
Thank you very much. Thank you.